Okay, now that you've gotten pretty good at inclined planes, it's time to make life a little more exciting. Now where we're going, but not today, but where we're going is, now that you're good at a box sitting on an inclined plane and sliding up or down, we're going to take that box and we're going to tie a rope to it. And we're going to run that rope up the incline over a pulley down the other side, and we'll eventually attach another block. So that's where we're going. But before we can get there, we have to look at ropes. Ropes, cables, strings have a special force that acts along them, and that force is called tension. And that's the little bit we're going to do today while the other half of the class is doing their lab. Okay, so we're going to look at tension in ropes, cables, strings, etc. Dental floss, fishing line, all of those things, okay? Now, in order to understand tension, you need to think about the rope. So I have a box, and I attach a rope or a string to it, so it's going around, and then I'm pulling it from this side, okay? And so what's happening here is I'm putting a force on this end, pulling it towards me, but I'm really only putting it on one section of the rope, this very end section. But the next end, that section is putting it on the next section, is putting it on the next section, is putting it on the next section, so that it gets passed down the rope until it gets to the object at the other end. So when we define tension, we simply say it's the size of a force that's exerted on, because I'm putting the force on this rope, but also by, because it's putting a force on the box. So it's a force that is exerted on and by a cable, a rope, a string, etc. And each section of that rope, cable, etc. equals is experiencing a force equal to the adjacent section, so that it passes the force down the rope. Okay, so it's a force whose magnitude is exerted on and by a cable, rope, and string, and each section of the rope exerts a force equal to what it experiences on the adjacent section, thus passing the force down the cable. Now, we have to make three assumptions when we work with cables, ropes, strings, etc. Assumption number one is that the rope is tiny, the mass of the rope is tiny compared to what you're lifting or pulling it with. So let's suppose I tie a tow rope from my car to the rafters in my classroom. So it's a nice, thick, huge rope. And now I am going to put a whiteboard marker, tie a whiteboard marker to the end. Okay? The mass of the rope is going to be really big compared to the mass of the whiteboard marker. And that's not a good thing. What we want to be able to assume in assumption one is that the mass of the rope or the cable is negligible compared to that of the load that's on it. So if I'm going to hang a whiteboard marker off the rope, then I probably want a piece of dental floss or a fishing line or something like that, something whose mass is going to be significantly small compared to the mass of the marker, that its mass is not going to have an effect on the overall system. The tow rope I would use to hang my car up. And if I was going to hang one of you from your belt loops up there, I'd use a rope somewhere in between. Okay, so the first assumption is that the mass of the rope is so much smaller than the load that it doesn't significantly affect the force or the motion and can be ignored. And this is a valid assumption as long as we pick our rope wisely, so that we don't hang a marker off a car's tow rope, but we hang it off a thin dental floss or something. Okay, so that's assumption number one. Assumption number two goes back to what I was talking about up when we first explained tension. Assumption number two is that the force of tension that gets passed down the rope is equal in all sections of the rope. So whatever this section is experiencing, it exerts it on the next one, which exerts it on the next one, and it passes it equally down the rope, so that each section is experiencing the same tension okay? And this is a valid assumption as long as your pet mouse has not gnawed at the rope. As long as the rope is not damaged, then it's a safe assumption to say each section will experience the same force, okay? So as long as the rope is uniformed and undamaged, assumption number 2 is fine. Assumption number 3 deals with a pulley. And I think you all probably know what a pulley is. So it's a round, circular, simple machine. We hang a rope over it. We maybe attach the rope to a box sitting on the floor, and then we grab the other end and we pull down. What does a pulley do? Really all a pulley does is change the direction of the force, right? I pull down on this side and the box experiences a force upward that's going to be equal to what I pull down with. Why would we do that? Because I can pull down and hang on this rope with all my weight and maybe get the box off the floor. If I need to move the box and lift it up, my only other option would be to come over here and bend over and try to pick this box up, and I'll be there forever in 2 days. So a pulley can make our lives easier. It doesn't increase the force at all. All it does is change the direction. And that is a valid assumption as long as our pulley is massless and frictionless. So as long as it's not huge compared to what we're doing, and as long as it's a nice smooth running pulley, it's not going to add or take away any force in our system. Okay, and so we will use this assumption too, so that all that a pulley does is change the direction of the force. All right, so we're going to start off easy. We're not going to connect too many objects to our rope yet. We're just going to connect one. So here's an example. It's an elevator filled with people that has a total mass of 3,200 kilograms. Okay? And it says that, sorry, I can't see it. It says that as it begins to rise, it accelerates. So it's going up and it's speeding up 0.55 meters per second squared. So acting down is the weight, and acting up will be the tension on the cable in the elevator. And the question wants to know, what is this tension in the cable? So guess what we're going to do? Sum of the forces in the y direction. But this time, the AY is not 0 because it's actually moving up and down. And there are no forces in the x direction. So what are my forces in the y? There's an FT and there's an FG. And the FT is what we're looking for. It's going up, FG is going down, so we'll make FG negative. And we're solving for FT, so take your FG over and it'll become MAY plus MG. So FT will equal, M is 3,200 kilograms, A is the 0.55 meters per second squared, plus 3,200 kilograms, times 9.81. Now notice I am not putting a negative on my 9.81. Just like all our other force questions, we looked after our negative up there when we put in our FG. Okay, so don't put it in twice. So 3,200 times 0.55 and then plus the next term that I can't say. I can say, but it just wouldn't come out. 3,315, 33152. I couldn't see where the decimal was. Newtons. That's if the elevator is accelerating upward. But now part B says, what if it was accelerated downward at the same rate? So this is A, and we're probably going to run out of time. But for B, it's still sum of the forces in the y. FT minus FG still equals MAY. So FT is still equal to MAY plus MG. The only thing that's different is now it's 3,200 kilograms, but the A is going down. So it goes in as a negative, 0.55 plus the 3,200 times 9.81. Okay, type this in. 3200 2963